Hello everyone, my name is Jing Yang. Today I'm going to present our TACL paper titled Self-Rationalization in the Wild, a large-scale out-of-distribution evaluation on NLI-related tasks. So why do we study self-rationalization? Self-rationalization is an explainability method where a model generates a label prediction and a natural language explanation. This method has been popular due to the user-friendly and easy-to-understand explanations. And why study auto-distribution? There are two major reasons. First, there's the number of datasets with annotated explanations are really scarce, causing challenging in learning and evaluation. And secondly, most LLMs are not really transparent in terms of training data, thus causing unreliable evaluation. And why do we focus on NLI-related tasks? NLI-related tasks actually includes family of many context-dependent reasoning tasks such as fact-checking and hallucination detection, which we consider very important in the era of large language models. Here, I present our evaluation pipeline. The evaluation pipeline consists of two parts. The first part is learning how to rationalize, self-rationalize. Basically, a model is fine-tuned to learn the self-rationalization task given a source dataset. For the source dataset, it is required that there will be abundant annotated explanations available. For this, we chose two different source datasets. The first one is ESNLI, where the context is small, which is premise, and contains human annotated explanations. We also have eFever, that is a fact-checking dataset, has much longer context, which is the evidence, and explanations are model-generated by GPT-3. Next, we study also how many data samples are needed for the self-rationalization task. We basically studied 5 different sample selection methods and 8 different sample sizes. And finally, we fine-tuned on 2 different open source models that has transparent training data. We made sure that the pre-trained data did not contain both ESNLI or eFever. The second step of the second major part of evaluation pipeline is OOD influence and evaluation. So for auto-distribution evaluation, we selected a diverse number of datasets, which has 9 NLI datasets, 6 fact-checking datasets, and 4 hallucination detection datasets. So in total, 19 datasets were evaluated based on a fine-tuned model, and then we are going to the evaluation stage. The evaluation is quite difficult in terms of explanations because the explanations were not annotated. Basically, there were no reference explanations available. For the labels, it is more straightforward as we can compare with the ground truth labels. Next, let's talk about the results on label prediction. The first results we have found is that fine-tuning data source actually has a large impact on auto-distribution label prediction. So first we show that the average F-score on the 19 datasets on ESNLI is almost 6 points lower than models fine-tuned on eFever. And here is a plot. It might be complicated, but what we want to show is that the results, the highest results the models can achieve on the 2 different source datasets are quite different. The second result we discovered is that the base model has a large impact, especially when the number of fine-tuning samples is small. So we highlighted the results from T5 and OLMo with different number of shots. Put it back to our figure. So especially when the number of shots is from 4 to 32, we see that OLMo performed much worse than T5 models for both source datasets. But eventually, OLMo actually has comparable performance and even outperformed T5s on eFever datasets. Our third result shows that fine-tuning on few shot samples have comparable performance with fine-tuning on the full shot, which is the entire training set. Here, we show a simplified results with only T5 full shot and OLMo full shot. So on the left is basically fine-tuning on the entire ESN NLI dataset training set, and on the right is fine-tuning on the entire eFever training set. And when we put back into the figure in comparison with different number of shots, we can see that the model on full shot is not really performing much better than on different number of shots, especially when we compare with 128 shots. Both OLMo and T5 are not outperform the few shots. And next, let's talk about the results on explanation generation. So how are the explanations evaluated? Since all of the 19 datasets are auto-distribution datasets without any reference explanations, we have to resort to different automatic metrics and human evaluation. For the automatic evaluation, we have 4 different metrics that are all reference-free. The first one is our proposed metric, Acceptability score. Acceptability score was originally proposed to filter out bad quality explanations generated by GPT-3, and they were fine-tuned on human annotated results to evaluate the explanations. The next 3 evaluation metrics are general large language model as a judge metrics that are fine-tuned on users' response on variety of different tasks. Next, we also performed human evaluation. Human evaluation was performed on 3 different datasets that are selected based on each of the categories: NLI, fact-checking, and hallucination detection. To cover different factors, we selected based on 13 fine-tuned models that has averagely similar label prediction performance. In total, more than 1,500 instances were evaluated by more than 460 crowd workers from Prolific. Here is a table showing the correlation between automatic metric and human evaluation results. We can see that out of the 4 metrics, acceptability score has the highest correlation with humans, despite being moderate. So the fourth result we have is that acceptability score actually is positively related to the label prediction performance. Here we show a figure from our paper that shows this trend. Basically, at the x-axis is the acceptability score and y-axis is a micro F1. Each dot in this figure is the average of 19 datasets from each model. We differentiate the source datasets based on different colors. From both source datasets, we can see a positive correlation between micro F1 and acceptability score, indicating that the explanation quality is positively related to the label prediction performance. For more results, please check out our paper. To conclude, we have the following takeaways. First, our results show that fine-tuning on a small amount of data can be as effective as many data points. And secondly, we show that our proposed metric, the acceptability score, has the highest correlation with humans, while the other 3 general large language models as their judge metrics were not as reliable. This indicates that to have reliable evaluation on specific generation tasks, we still need tailored metrics. And last, our results also show that the explanation quality indicated by our acceptability score is positively related to the label prediction performance, in contrary to some study that shows that there is a trade-off between explainability and task performance. Thank you very much for your time. We'll present our work at ACL 2025 in Vienna. Looking forward to seeing you there.